Now, in the crossover, once again, just picking up where we left off, okay, and we had, in the case of functions from last time, and we looked at functions in the capacity of looking at types of ordered pair sets. And again, for a function, by definition, okay, a function is going to be a mathematical relation where in the xy coordinate system, we have for each x value, there's going to be one and only one y value that is going to correspond. And again, all ordered pairs are of the form xy. And again, x is going to be referred to as the independent or input variable. And in the case of y, okay, that is going to be the dependent or the output variable. And again, when we looked at samples of ordered pairs that might be functions or not, and we had like among our cases, say if you have like -1, 1, 3, 4, and 5, 7. Again, we had this to be a function because for each x value, there's going to be only one corresponding y value. And you have with the domain, you have the set of x values, which we have with -1, 3, and 5. And with the range, you have the set of y values, which we have with 1, 4, as well as 7. And again, anytime you have a repeating x value and the repetition is with a different y value, then you're not going to have a function. And so again, anytime you have repeating x values and the repetition happens to be where x is paired up with a different y value, it is not a function. And again, we have where we have functions, again, for each x value, there's only one corresponding y value. And just to sort of reaffirm what we have in the case of working with functions, and we have in the realm of graphing. Okay, so we have in this particular situation. Okay, so we're going to have. Okay, so we have in. What we have now. Let's see if we get my. There we go. So we have in graphing, a function is going to satisfy what is referred to as the vertical line test. And in the case of the vertical line test, okay, what this is going to mean is that a vertical line will intersect the graph of a function . At most. One point for all x values. Okay, so vertical line test, you have a vertical line, not just a vertical, but a vertical line. Okay, so a vertical line will intersect the graph of a function at most 1 point for all x values. And this might seem a bit wordy, but just to kind of bring it to life. Okay, say if you have determined whether the graph is going to be a function or not. And I'm going to sort of do some quick sketches. It's kind of taking the X and the Y, the XY coordinate system. Okay, so you have with the X-axis and Y-axis. Again, we have with the X-axis. Okay, we have a number line that is going to run horizontally. Y-axis, you have number line that is going to be running vertically. And I'll just go ahead and copy this. Okay, and let's say if we have a function or not. And let's say if we have y is equal to f of x. Now I'll explain the f of x in just a moment. But let's say we have y is equal to 2x plus 4. Okay, and if I'm applying the vertical line test, okay, and I'm running it through the graph. Okay, so if you notice going from end to end, I have intersection at one point, and as I continue along what I have for x, I still have at most the intersection at one point. So y equals 2x plus 4 is going to be a case of a function. Now let's say if we have as another case here, and we'll say that we have maybe not specifying. Let's say if we have some line segments in the mix. And I ran a vertical line through this, through all of these. Okay, so we have here, so if I start to run through, okay, and get near the first line segment, okay, so you have intersection at most 1 point. Now there's no intersection here because there's a gap or spread between the line segments. But again, just running through, still intersection at most 1 point. Now we have no point. And again, just for all x values, okay, you're going to have intersection at most 1 point. And so this is a case of a function. And let's say that if we have something like say we have a circle. And we'll say that it is going to be centered at the origin. And this circle, okay, so we'll say we have, we'll cross the x-axis at negative 2, 0, 2, 0, and the y-axis at 0, 2, and 0, negative 2. So you have the center at the origin, and the circle is going to have a radius of 2. And we'll say that this will be represented by the equation. So we have x squared plus y squared is equal to 4. And to see if this is going to be a function or not, Okay, so again, if I apply the vertical line test, okay, say if I have approaching the edge point, -2, 0. Well, guess what? Once I start to move the least bit to the right, now I got the same exit value, say where this vertical line ceases. But if you notice, okay, we have at the same x value, I have the intersection between the circle and the vertical line at 2 points here. And so you got 2 points of intersection at the same x. So in this particular case, for this circle, this one is not a function. And the reason for this is that you had the same throughout, say between the edge points, -2, 0 and 2, 0. Guess what? The upper and bottom halves happen to intersect the vertical line, okay, at the same x value. Okay. So a circle is not a function. And one might pose a question, like if I took out, okay, because you have like both halves are interfering with each other and are thus preventing the circle from being a function. And it says, well, you know, if you have two halves and I make it like the graph into half of it, you might pose a question, can half a circle, or in this case, can a semicircle be a function? And to sort of answer this question, say we take the right half. Here we go. Okay, so you have like the semicircle, and say for the right half, this would be like in the case where we have the x is equal to the square root of 4 minus y squared. And if I try, again, running a vertical line through this. So once I get past the y-axis, we can have the problematic situation where we have 2 points of intersection at the same x value. So this semicircle, okay, again, that one is not a function. But let's say if I give, like you can say from here, say if I give it like a quarter turn. All right, so we're about like 3/4 of a turn. So you have quarter turn. Okay, so we got in this one. So you have 2, 0, 0, 2. And -2, 0. So we have here And if I run a vertical line through this, okay, so if I go from end to end, okay, on the basis that we had an official semicircle drawn, if I had to sketch this one, this feature doesn't quite do the semicircles as it does neatly with the full circles. And I can't just cut out the lower half so automatically, but here we have the intersection at most 1/2, and this semicircle will be like an illustration of y is equal to the square root of 4 minus x squared. And because we have the intersection at most 1 point, okay, this one is going to be a function. So just going back to the question in terms of whether a semicircle can be a function, the answer to that question is yes, and it depends on the layout. In other words, like if you had like the right half or the left half of a circle, it's not going to be a function. But if you're looking at upper half exclusively, or just the bottom half or the region beneath the x-axis exclusively, then that semicircle would be a function. And then just we'll take this, kind of use this as a separate case here, like in terms of determining whether we have a function or not. And if I were to include say yet another line segment, and ran the vertical line through this, okay, so again, at each x value, there should be only one corresponding y value. And guess what? We have like this among others. We got 2 points of intersection. And so before I had a function, but with the inclusion of this particular line segment, okay, there's a bit of chaos that is created. So this is not a function. All right, now, again, so with functions, okay, for each x value, there's only one corresponding y value. And again, a function is going to satisfy the vertical line test, which in its xy coordinate system way reaffirms that for each x value, there's only one corresponding y value. Now, for that f of x notation, so we have with functional notation, again, so we have, and it doesn't have to be limited to just f. It could be y is equal to f of x, g of x, z of x. And in the case of y is equal to f of x, okay, now again, x is the input or independent variable. And we have for y is going to be the output or the dependent variable. Okay, so f of x, if you see that, that's just another way of saying y. Okay, I've never been asked this question before, but again, I say that you could have a different letter like g of x, h of x, z of x, and one might ask, well, could it not be just y of x? And the answer to that question is sure. Yeah, because in fact, for some calculus sequence courses, where you might just have like y is equal to whatever there is in x, you might see the solution to be not in the form of y equals, but y of x is equal to. So that f of x could just as well be y of x. And now, for what we have regarding functional notation, and we have just a kind of a brief crossing over to determining functional values and expressions. Now let's say we have a case of a function. And let's say we have given say y is equal to f of x. And we'll say we have is equal to x squared minus 3x. And you were to determine, let's say, f of negative 3, as well as f of 1. And say we have, looking at the determination of f of x of 2. Okay, so just in the layout, okay, so you have f of x equal to x squared minus 3x. Again, we have a quadratic function. Okay, so you have f of x is referenced to y. So you have y is equal to x squared minus 3x. So you have in the pattern, f of the input is equal to the square of the input minus 3 times the input. Now with f of negative 3, if I change the general input x to the specific value of negative 3, where the output is going to be upon using the input of negative 3 is going to be the square of negative 3 minus 3 times negative 3. And the square of negative 3 is going to be 9. Negative 3 times negative 3 is going to be another positive 9. And 9 plus 9 comes out to 18. And so what this means is that we started with x equal to negative 3. And we had that y was equal to 18. So among the points that would be on the graph of y is equal to x squared minus 3x, negative 3, 18 would be among those ordered pairs. Likewise for f of 1. Okay, so the input we have at 1, so we have in the follow through, so you have the square of 1 minus 3 times 1. 1 squared is 1, negative 3 times 1 is minus 3, and 1 minus 3 comes out to negative 2. So here we have x equal to 1, and y equal to negative 2. So not only would negative 3, 18 be a point on the graph, but also we would have 1 and negative 2. Now, if I go from going from one variable expression out to another, and say instead of the input, variable input at x, if I change the x to x plus 2, what would the output become? I'm still going to operate with x plus 2 in accordance with what is prescribed, for f of x. So with the input at x plus 2, so we'll be looking at taking the square of x plus 2 and have minus 3 times the quantity of x plus 2. So again, whatever's in parentheses, I'm going to square out and then take minus 3 times what was in parentheses. And just a reminder, okay, so again we have with the square of x plus 2. The easy part to remember is taking the squares of x and 2. But remember, this happens a lot. Many forget that there are outside and inside products to add together. So you have not just x squared plus 4, but you can have x squared plus 2x, which will be 4x. So we have in following through. So for the square of x plus 2, we have x squared plus 4x plus 4. Then for negative 3 over the quantity of x plus 2, we're going to have negative 3x minus 6. And then we have upon combining like terms together. Okay, so then we have x squared, 4x minus 3x. Okay, so this will leave us with plus x. And 4 minus 6 is going to end up at negative 2. So we come out to x squared plus x minus 2. All right, and tell you what, just for the next few moments, let's say if we have given a function and say we have f of x is equal to 2x squared minus 3x plus 7. Okay, let's see what we get for we say we have f of negative 3 once again. And we'll say we have determining f of 5 and also f of x plus 1. So be looking at these 3 items and we'll discuss in just a few moments. Okay, if we look into what we have for this function, so we have f of x is equal to 2x squared minus 3x plus 7. And again, f of x is another way of saying what we're going to have for y. And we have with the first 2 items, we're looking at what the y value is going to be whenever x is equal to negative 3 and also whenever x is equal to 5. So with x at negative 3, your y value that corresponds is going to be the result from taking 2 times the square of negative 3. And we have minus 3 times negative 3, followed by the addition of 7. And here we have 2 times. Now the square of negative 3 is going to be a positive 9. And we have negative 3 times negative 3 becomes a positive 9. And we have plus 7. And we have in following through, so you have 2 times 9 is 18. 18 plus 9 is 27, and 27 plus 7 comes out to 34. So whenever x is at negative 3, the corresponding y value we're going to have at 34. And whenever x is at 5, so again, so you have 2 times the square of 5. We have minus 3 times 5. Followed by the addition of 7. Okay, now we have 5 squared is 25. So you have 2 times 25. Negative 3 times 5 is negative 15. And we have plus 7 to tag along. And we have 2 times 25 is 50. Minus 15 will make 35. And 35 plus 7 comes out to 42. So a couple of points we have on the graph of y is equal to 2x squared minus 3x plus 7 will be negative 3, 34, as well as 5, 42. Now, for the general expression that we have going from x to x plus 1, if we're looking at what the variable expression output is going to be, So I'm going to have 2 times the square of x plus 1 minus 3 times the quantity of x plus 1 and we have followed by the addition of 7. So we have for 2 times the square of x plus 1. So we have 2 times, again, x plus 1 times x plus 1 is going to be x squared plus 2x plus 1. For negative 3 over the quantity of x plus 1, we have, upon removing the parentheses, we have negative 3x minus 3. Yeah, plus 7. And we'll just move on down. Okay, so taking care of the distribution and removing the parentheses. So we have 2x squared plus 4x plus 2 will be at the front. We have minus 3x. And from minus 3 plus 7, I can just go ahead and combine these terms. Negative 3 plus 7 comes out to plus 4. And here we're going to have 2x squared. Now 4x and negative 3x will be a positive x. And we have 2 plus 4, which is going to be at 6. So by adjusting the input from x to x plus 1, the output changes over to where we have 2x squared plus x plus 6. Okay, now once again, going back to the features of functions and sort of pinpointing upon the term domain. Again, domain is going to be the set of x values. And just for what we have in the case of taking what we have for domain, okay, and we have for the domain of a function. And again, we'll just identify the function as y is equal to f of x. Now for the domain of a function, y is equal to f of x. Again, you have, for the domain, you had the set of all x values. Now when we looked at the sets of order pairs, now the x values were already laid out. But let's say if you have the function like f of x is equal to, it could be like a fraction in the variable x, or it could be like something like x squared minus 3x plus 4. And there might be or there might not be a limitation in terms of what x can be. And for what we have here, now we do know that domain is going to be the x values, but just to kind of expand the model, this is going to be the set of all x values such that f of x is defined in the set of real numbers, all real numbers. And again, just for the interval notation for all real numbers, again, you have parentheses around negative and positive infinity. And for the domain of a function, say if I'm looking at determining the domain using interval notation. And we'll say we have as our first case. Okay, we'll say that we have f of x is equal to 3x plus 7. Okay, so we have our variable term at 3x. Okay, now for x, x could be 0, and if this were the case, we have f of 0 be equal to 7. And if I had x as a positive, okay, I'll still have a defined value for f of a positive value. And if x were negative, I'll still have a defined value for f of x. So there's no limitation in terms of what x can be. So x has no restrictions. So what's going to result here is that for the domain of the function, okay, that's going to be the set of all real numbers. And the interval notation, again, you have parentheses around negative and positive infinity. And if I have, let's say, f of x is equal to x squared minus 4x minus 17. Again, x is given in direct fashion, and there's nothing like a fraction or an even root radical to keep x from being 0 or a positive or a negative. So while we have an entirely different function in comparison to the first case, we have, in terms of the domain, you have history to repeat itself, again, because there are no restrictions placed upon x. We have, once again, the domain will be the set of all real numbers. Now let's say that if we have f of x such that f of x is equal to 3x plus 4, then we have all over x minus 5. Okay, now this time x cannot be just anything. Okay, and the reason for this is that, okay, for this function to be defined, okay, we cannot allow for the denominator to be 0. So there is a restriction, and it's going to be that x minus 5 cannot be 0. So left out is going to be the value of 5. And just to kind of give you a visual. And it's a little bit tedious, but it's nothing like that. Some of the stuff we dealt with the absolute value inequalities. But again, the centerpiece, okay, you have 5. And 5 is going to be left out. So you have a hole on 5. But the solution will be everything else. So you have at one end of the spectrum, you're looking at those values that will be less than 5. And at the other end, you'll have those values that will be greater than 5. And so for what would be the domain in this particular case? Okay, so we'd be going from negative infinity, approaching but not including 5. And the exclusion of 5, okay, will be, again, using parentheses. Okay, so this segment or section less than 5, okay, represented by this interval notation, and then we have in union with the half, okay, that is greater than 5, and that's going to be denoted by parentheses around 5 and going continuously out to infinity. So that will be the interval notation for the domain of this particular rational function. And if we have so So we have f of x is equal to 2x squared plus 3 all over x squared minus 16. Okay, so again, have another rational function, and this time, again, we're still disallowing the denominator from becoming 0 in value. So now we have x squared minus 16 cannot be 0. And if that is the case, then anything that forms x squared minus 16, namely its factors, cannot be 0 either. So if we have, let's say that x plus 4 cannot be 0, we have that x cannot be negative 4, and if x minus 4 cannot be 0, so we have that x cannot be equal to 4, so we have with our excluded values of negative and positive 4. Again, on negative 4 and 4, if I were to graph, okay, so I have like graphing or symbolizing exclusions, again, just have holes on negative and positive 4. And everything else would be in the domain. Okay, so for what we have with the extremes and everything else in between, okay, so we have for the interval solution, okay, so for the domain case, so smallest set of values you have proceeding from negative infinity, approaching but not including negative 4. So you have parentheses. And then for the section in between, you have those values of x such that negative 4 is less than x, which in turn will be less than 4. So I still have parentheses indicating the exclusions of negative and positive 4. Then for the last section, you'll have those values that will be greater than 4. And so we have, again, parentheses around 4 and infinity. And I'm just going to mention, notice before we had one exclusion from which we had drawn forth two interval sections when expressing in terms of intervals for the domain. And notice you had two exclusions leading up to three subset or subinterval sections. And had I ended up with a third exclusion, say if x could not be negative 4 or 0 or 4, then I would have had 4 subinterval sections indicating the exclusions of like negative 4, 0, as well as 4. Alright, so you do have exclusions potentially in the domain if your function happens to be a fraction and you have restricted values, okay, that would otherwise create a 0 denominator in the ratio. Now, and the other situation could be where you would have, let's say, a function set equal to an even root of an expression in the variable for the input variable. And say if I have f of x is equal to the square root of x minus 7. Okay, and because we're dealing with a square root, you have like x minus 7 cannot be negative inside of even root. like it could be negative, like in cubic roots, fifth roots, seventh roots, but for stuff like second roots, like square root or fourth root or sixth root, whatever's inside cannot be negative. Okay, so, and now you can have the square root of 0. So x minus 7 can be 0, and x minus 7 can be positive. So just kind of creating the path forward to solving for x. We can set up an inequality. So we have x minus 7 is greater than or equal to 0. And upon isolating x, if I add 7 to both sides, we'll have that x is greater than or equal to 7. Again, you don't have to graph it, just looking at it visually. So you have the number 7 involved. And with the nature of the inequality, greater than or equal to 7. So the equal signals that we have a close point, not a whole, but a close point on 7, indicating that 7 is included. Then the rest you have to be greater than, so we're going to have array to go continuously to the right. And approaching infinity. And so for what we have in this case, and that's an interval, but I just wanted to we're looking at domain, still an interval. And for the domain here, so we're going from and including 7. And we have approaching infinity. Okay, so for this rather short or terse statement in comparison to the previous two examples, that is going to be the solution in interval notation. And just kind of serving as a reminder. If we have, let's say, f of x is equal to the square root of 8 minus 2x. Again, for the same reason, we have the encounter with an even root radical. So 8 minus 2x cannot be negative. And just for the setup and finding out what values of x will keep f of x as a real function. Okay, so 8 minus 2x, it can be 0 and it can be positive. And looking at isolating the x term. So if I take 8 away from both sides, so we're now going to have negative 2x is greater than or equal to negative 8. And if I solve for x, okay, so again, be careful. If you're multiplying or dividing, not adding or subtracting, but if you're multiplying or dividing by a negative, remember to change the direction of the inequality. So again, we're going from greater than or equal to less than or equal to. So the inequality solution for x is going to be that x is less than or equal to 4. Okay, so you have just one value to work with. Okay, so you have 4. Again, just like the 7 earlier, 4 is included, so you have a solid point. However, everything else is going to be less than, so we're going to go in the other direction. We're going to the left, and we have the values decreasing. We have down to the depths of where we have approaching negative infinity. So we have for the domain for this item. Okay, we're looking at going from negative infinity and approaching and including the value of 4. And 4 is included, and that is going to be placed in the bracket. Right. And let's say if we have kind of a twofold situation. And we'll say that we have that f of x is equal to, and we'll say that we have f of x is equal to x minus 13 all over the square root of x plus 10. So you have a twofold situation here, one of which we have most recently working with the square root or an even root radical. So again, inside the radical we have x plus 10. So x plus 10 cannot be negative. And also because x plus 10 is in the bottom of a fraction. So we had the x plus 10 cannot be 0. Okay, so if x plus 10 can't be 0 and if x plus 10 can't be 0, but the only remaining category we have is going to be that if x plus 10 can be anything else, well, it must be positive. And the inequality referencing x plus 10. So if x plus 10, if the sum has to be positive, well, x plus 10 must be greater than 0. And looking at isolating x, so if we take 10 away from both sides, we're going to have the x is greater than negative 10. And it's kind of going back to quick sketch. Okay, so you have, again, the value of immediate concern. Okay, we have it negative 10 and with greater than negative 10. So you have negative 10 is not included, so you have an open circle. And so we have, for the activity, you have a ray that's going to go out to the right and will cross over into the positive threshold and approaching infinity. So for the domain of this particular function, we have, again, for the set of all values of x greater than negative 10, so we have a parenthesis around negative 10, and we have approaching infinity. And again, infinities are boundless, so the interval solution in the domain we have consisting of only parentheses. All right. Okay, I know that it was kind of tedious, but again, just some reminders. If you don't have all real numbers for the domain, again, you might have individual restrictions from fractions and from radicals, and also, like this last case, you might have a combination of restrictions regarding the algebraic expression. Now, just some things here. We're going to cross over to from expressions to equations. And now, and from functions. Okay, we're going to be, a lot of stuff is going to be recycling or repeating. And we'll be looking at various types of equations in two variables. And one of the key foundations, okay, that we have for linear equations in two variables, such as x and y, okay, we're going to have slope. Okay, and for the slope of a line, okay, and for slope of a line, now the slope of a line, that's going to run through 2 points. So I'm going through 2 points. So you have x01, y01. And so we have x02, y02. It's going to be, okay, so you have, now for the letter we're going to use to represent slope. Okay, we have the letter M, and we have this equal to y02 minus y01. All over x02 minus x01. Okay, and so you're looking at vertical change with respect to horizontal change. And for x02 minus x01, again, for the slope to be defined, okay, the bottom part cannot be equal to 0. Again, for the slope to be a real number. And, okay, and just some things to mention now. Technically, x01 and x02 cannot be equal. So you have, if x01 and x02 happen to be equal to each other, and I'm just kind of use some arrows, okay, just to kind of show the domino effect. Okay, so x02 minus x01 would be equal to 0. And if that were the case, well, you have the fraction to consist of a 0 bottom number. Okay, so the slope would be undefined. Okay, and if you have a line with an undefined slope, okay, what's going to happen here? Say if your x is not moving, but the only motion you would have would be between the y values, and guess what? It would either be moving up or down. So a line that has an undefined slope is going to be vertical. Okay, now let's say that just a case of where you're going to have a defined slope. Now, so you have a couple of points here. I'm just going to go ahead and label. Okay, so you have -1, -4. Now say I have going out to 3, 6. And that these 2 points are connected by a straight line. Okay. Now let's say that you were to determine the slope of a line passing through the points -1, -4, and 3, 6. Okay. Now again, just for the setup, okay, now if you were to go through the process of using the slope formula, you want to go ahead and specify what your first and second x and y sets are going to be. Okay, so just specifying, so we have -1, -4. We'll say that since that one is given first, we can let this represent the x1, y1 combination. And with 3, 6, we'll let this be the second set. But it could be the other way around. We have 3, 6 as x1, y1, -1, -4 as x2, y2. And so just filling in. So for y2 minus y1, your y2 is at 6. Minus y1, so we had the subtraction of -4. And all over x2 minus x1, so your x2, we have at 3. Then minus x1, so we have subtraction of -1. So we're going to have 6 plus 4 all over 3 plus 1. 6 plus 4 is 10. 3 plus 1 is 4. And the ratio in the slope, okay, this can be reduced to 5/2. Okay, so for what we have, okay, so the slope is going to be 5/2. And again, this would be just like if you were to look at a pattern, so the top portion is vertical. So you could look at this as up 5 units, and for the denominator, you're looking at shifting x values, and with the positive 2 change, you see have up to the 5 and going out to the right 2 units. And if I were to take what I have, let's say with these 2 points, kind of form like a staircase or triangular schematic. Okay, so I had -1, -4. So if I go up 5 units, and let me zoom in on this. Okay, so you have for this particular layout. Okay, so if I were to go up 5 units, so starting, so going up 1, 2, 3, 4, 5. Okay, so I'm at y is equal to 1, and if I go over 3 units, say from x at -1 to x at 0 to x at 1. So I'm going up 5 units and out to the right 2 units. I want to have, say like as an intermediate point, this would be x at 1, y at 1. And if I continue the same trend, say going up 5 units and out to the right 2 units, I would be at 3, 6. But again, in the overall scale, I went up 10 and to the right 4 units. Okay, but again, just the granular incremental breakdown is the cycle of going up 5 and to the right 2 units. And so think of it kind of like a staircase. And you're kind of going to the same destination. If there's an endpoint, if the line continues to a final destination. But again, to stay on the line, from everything before -1, -4, and anything coming after 3, 6, you want to maintain the cycle going up 5 and to the right 2, or again, which complies with the slope value of 5/2.